Hi everybody, so this is lesson 2.5 and it's the second part of our lesson on integration by partial fractions. So in this lesson we're going to talk about two specific scenarios with the factors that come up in the denominator when we're integrating. So in our first lesson we always had neat and tidy factors, whether it was x plus 1, and so let's say x minus 2. They were all terms that just had x, okay? They weren't x squared or x cubed, and they were all different. So the first scenario we're going to look at is how to set up the partial fractions when we have two of the same factor. So x minus 1 squared, as an example, factors out to x minus 1 times x minus 1. So it's the same factor. That's scenario 1. Scenario 2 is if we have a quadratic, okay? So something like ax squared plus bx plus c, and we cannot factor it any further. An example of this would be x squared, let's say, plus 4x and minus 6. We can't factor that with factors that give us positive 4 when they're added up and multiplied to negative 6. So you can't factor that any further. So there's small tweaks to how we set up the partial fractions, but the remaining algebra remains largely the same. I'm going to show you a slightly different way in this case where we find out the coefficients, so the a, the b, and the c terms if there's 3. But otherwise, in general, you'll be performing the same algebra. So let's look at our first case. Okay, I'm going to use the same example you saw. The integral of 2x plus 1 divided by x times x minus 1 squared. So x minus 1 squared is actually x minus 1 times x minus 1. Okay, so it's two of the same factor multiplied together. So when we set up the partial fractions, we do it almost entirely the same, where we have a divided by the first factor, x, plus b divided by the second factor, x minus 1. But we have a plus c divided by, instead of just x minus 1, it's x minus 1 squared. Okay, so for each duplicate factor, you have to then add the exponent. So if this was x minus 1 cubed, we'd have a third term that was d divided by x minus 1 cubed. Okay? So that's the major difference when you have repeating factors. Other than that, the math remains the same. Okay? So looking at this example, I want to show you how to solve it. Okay? So we have our three factors, and we're going to go about it the exact same way. So our first step is to remove the fractions. And we do that by multiplying both sides, it's a bad x, by all three factors, x times x minus 1 times x minus 1. Okay? So when you do that, on the left-hand side, the factors all go away. We have 2x plus 1. And on the right side, the first factor, a, all right, is a times x minus 1 squared, right? Because the x term is the only one that cancels. For b, we have b times x and x minus 1, because the only term that cancels is one of the x minus 1 terms. And for c, both x minus 1 terms cancel, but the x term remains. So we end up with plus cx. Okay, so in this case, we have a couple options that we could look at here. Okay, the first option I'm going to show you is the way we've done it in the past. What you'll notice here, the big difference is we only have two factors that actually make one or two of those terms go to 0. And those would be if x is 0 or if x is 1. So if we follow the exact same way for doing those, we can get our first two factors. Our third factor, we would have to substitute a different value of x in. Okay, it doesn't necessarily have to zero it, but since we've solved for all the factors at that point, except for one of them, we can still solve. So let's start by finding the first two factors. If we sub x equals 0, we get 2 times 0 plus 1 is equal to a times 0 minus 1 squared plus b times 0 times 0 minus 1. You'll see that this term will then cancel because it's multiplied by 0, plus c times 0. Again, the third term would cancel. So 2 times 0 is 0, and we're left with just 1 is equal to a times negative 1 squared. So a becomes 1, okay? Because negative 1 squared is positive 1. So we have 1 equals 1 times a, which just means a is 1. So now we can substitute x equals 1, our second factor. And we're left with 2 times 1 plus 1 is equal to, a is 1, multiplied by 1 minus 1 squared. You can see that 1 minus 1 is 0, so that term will cancel. Plus b times 1 minus 1. Okay, again, 1 minus 1 is 0, so this term would cancel. Plus c times 1. So on the left-hand side, 2 times 1 is 2, plus 1 is 3. So we're left with 3 is equal to c, okay, because it's just c times 1. So c is just simply equal to 3. Okay, so now we have the a term and the c term, but we don't have any, like I said, any other factors to substitute in. And it's okay at this point to be like that, because now if we look at our equation, we have 2x plus 1 is equal to a, which is 1, times x minus 1 squared, plus bx times x minus 1, plus 3 times x, substituting those values in. So we only have one more term that we have to solve for. So we can substitute of any value of x. It's usually easier to substitute a smaller number in. Okay, in this case, I'm going to try x equals 2. And you can simply solve now, because our only unknown then, substituting a value of x in, would be b. So I'm going to another slide, just to make it a little bit cleaner, since we have the last term. But I again will write out what we have. So we have 2x plus 1 is equal to 1, because we solved for a, times x minus 1 squared, plus b times x minus 1, plus 3x. Okay, so I picked x equals 2. So we're going to sub x equals 2. Okay, just a value of x, because these equations have to be equal. Okay, one side has to equal the other. You could substitute any value of x in here, and you should be able to solve for b. So we have 2 times 2 plus 1 is equal to 1 times 2 minus 1 squared, plus b times 2 minus 1, plus 3 times 2. So on the left-hand side, we have 2 times 2 is 4, plus 1 is 5. And that's equal to 1 times 2 minus 1 is 1 squared. So that's just 1. Plus, in this case, we have 2 times 2 minus 1. So this just leaves us with 2b, plus 6. So if we're trying to solve for b, okay, we have bringing the remaining terms to the left-hand side. We have 5 minus 1 minus 6 is equal to 2 times b. So if we do the math on that, we get negative 2 is equal to 2b. So dividing both sides by 2, we get that b is equal to negative 1. So now we have all the factors. Okay, I'll write them just in the corner here. We have a is 1, b is equal to negative 1, and c is equal to 3. So if we substitute those in, all right, we get 1 over x minus 1 over x minus 1 plus 3 over x minus 1 squared. Okay? So we can substitute that into our original integral. Okay, so now it becomes, move it over here, the integral of 1 over x minus the integral of 1 over x minus 1 plus the integral of 3 over x minus 1 squared. Okay? So the first two factors look just like what we've done in the past, where they then become ln of that function. The third one looks a little bit different. And the easiest way to see that is you write that, okay, as a negative exponent instead. So this can be rewritten as 3 times x minus 1 to the exponent negative 2, right? So that's if you move the function from the denominator into the numerator. And that formula, or that format, is just using the power rule. So remember, the power rule was the integral of a function x to the exponent n is equal to 1 over n plus 1 times x to the n plus 1. Okay, so we can use that to solve for this. So what this means is we have it equal to, the first two integrals are just like the ones we've seen in partial fractions. Ln, and then it's of the function in the denominator, so the absolute value of x. Second one is the same, minus the ln of the absolute value of x minus 1. The third one is now 3 times x minus 1, and it's the exponent negative 2 plus 1, again, using the format for the power rule, divided by negative 2 plus 1. So if we sum that up, we get the ln of x, again the absolute value, minus the ln of x minus 1. And then here we have 3 divided by negative 2 plus 1. Negative 2 plus 1 is negative 1. So that leaves us with minus 3 times x minus 1 to the exponent negative 2 plus 1, which is negative 1. Okay? And that is plus a constant. So you're going to see when you end up with integrals like this that have repeating factors, you're going to end up with another term in here that looks something like this, okay? Depending on what the x minus is, whether it's x plus 2, x minus 1, and whether or not we have a constant here, okay, when we solve for the partial fractions. All right? So let's look at one more example of repeating factors before we look at the second case. So evaluate the integral of x divided by x plus 3 times x squared plus 4x plus 4 dx. So we have to start by factoring this x squared term if we can. And we can, because you can see that the options we have to multiply to positive 4 would be plus 2 and plus 2, plus 1 and plus 4, or the negative alternatives to that. Well, you add up these factors, plus 2 is plus 4, and 1 plus 4 gives us plus 5. Well, we see in the middle here that the value is plus 4. So we can rewrite this integral as the integral of x divided by x plus 3 and x plus 2 and x plus 2. So you can see that we have two of the exact same factors here. So because they're repeating, we have to do the same slight tweak to partial fractions that we did in the previous slides of this lesson. So we can write this out as partial fractions. So we have x divided by x plus 3 times x plus 2 and x plus 2. And we write it as a divided by the first factor, x plus 3, plus b divided by the second factor, x plus 2. And remember, since it's repeating factors, our third factor is plus c divided by that repeating factor. So x plus 2, but squared. All right, so again, that's the major difference when it's repeating factors. So just like we did in the last example, our next step is to remove the fractions. And we do that by multiplying both sides by all of the factors. So we have x plus 3 times x plus 2 times x plus 2. And we do that to both sides. Okay. So these factors will cancel on the left-hand side. And what we're left with is x is equal to, on the right side, we have a multiplied by, in this case, just the x plus 3 term will cancel. So it's a times x plus 2 squared plus b times, in this case, just the x, one of the x plus 2 cancels. So we have x plus 3 and x plus 2. And then the last term, we have plus c, and the only term that doesn't cancel, the x plus 2's both cancel, so we're left with just x plus 3. Okay? So again, just like in our last example, there's only two factors here. There's when x is equal to negative 2, it'll zero these factors. And when x is equal to negative 3, okay, those are the only two factors we can use. So we do those, solve for those two terms, and then we can substitute a different value in for x to solve the remaining term. So we'll start with x equals negative 2. And what we're left with is negative 2 on the left-hand side is equal to a times negative 2 plus 2 squared. You'll see that that gives you 0, so it will cancel. Plus b times negative 2 plus 3 and negative 2 plus 2. Again, negative 2 plus 2 is 0, so that one will also cancel. Plus c times negative 2 plus 3. So what we end up with here is just negative 2 on the left-hand side. And on the right-hand side, we have negative 2 plus 3, which is positive 1, times c. So we're left with just c. So our first factor is c, which is equal to negative 2. Our next factor we'll use is we'll substitute in x is equal to negative 3. And if we do that on the left-hand side, we have negative 3 is equal to a times negative 3 plus 2 squared plus b times negative 3 plus 3 and negative 3 plus 2. Again, you'll see a negative 3 plus 3, which is 0, so this term will cancel. Plus c times negative 3 plus 3. Okay, again, this term will cancel because negative 3 plus 3 is 0. So what we're left with is negative 3 is equal to, we have negative 3 plus 2, which is negative 1 squared. That gives you positive 1. So our next value is negative 3 is simply equal to a. Okay. So again, our last one is we have two of the factors, so we have to pick a value of x. I always pick the easiest value I can. In this case, why don't we just pick x is equal to 1? Okay, so if we do that, we have x is equal to 1. Then on the left-hand side, we have 1 is equal to a, which is negative 3 times 1 plus 2 squared, plus b times, in this case, we have 1 plus 3. Again, 1 plus 3 and 1 plus 2. And then we have c is negative 2, so minus 2 times 1 plus 3. Okay? So if we start to simplify these, all right, what we end up getting is 1 on the left-hand side is equal to 1 plus 2 is 3. Okay, so 3 squared is 9. So the first term is negative 27. The second term is 1 plus 3 is 4, and 1 plus 2 is 3. So those combine to give you 12. So we have plus 12 times b. And our last term is negative 2 times 1 plus 3, which is 4. So we end up with negative 8. So if we solve for this, if we move those two constants to the left-hand side, we're left with 27 plus 8 plus 1 is equal to 12 times b. So 27 plus 8 plus 1 is 36. So 36 is equal to 12 times b. So solving for just b, we divide both sides by 12, and we're left with b is equal to 3. So now we have all of these factors, okay? So I'm switching to the other slide again, starting with what we had initially. We had the integral of x over x plus 3 times x plus 2 and x plus 2. And now we can write this in terms of what our partial fractions were. It's equal to the integral of the a term, which is negative 3 divided by x plus 3, okay, plus the integral of the b term, which is 3 divided by x plus 2, and plus the c term, okay, which is negative 2 over x plus 2 squared. Okay. Remember, for the term that's divided by the squared, you can rewrite that as negative 2 times x plus 2, and it's to the negative exponent. Okay. So looking at each one of these, the first thing I like to do is I like to move all of the constants out of the integral. So to do that, I have negative 3 times the integral of 1 over x plus 3 plus 3 times the integral of 1 over x plus 2 minus 2 times the integral, and I'm going to write this like I did right here. So we have x plus 2 to the negative 2. So now with each of these forms, we can now take the integral of them individually. So we end up with is negative 3 times the ln of, remember, the item that's in the denominator here, which is x plus 3, and it's the absolute value, plus 3 times the ln of x plus 2. And our last term is minus 2. Remember, we have x plus 2 to the exponent negative 2 plus 1 divided by negative 2 plus 1. Remember, that's because we use the power rule, which is the integral of x to the n is equal to x to the n plus 1 divided by n plus 1. Okay? And our last term, obviously, switching back to my other color, would be plus a constant. So if we keep going, we have negative 3 times the ln of x plus 3 plus 3 times the ln of x plus 2, both absolute values of ln. And our last term becomes negative 2 divided by negative 2 plus 1 is negative 1. So two negatives make a positive. So we have plus 2 times x plus 2 to the negative 1. You can also write this as 2 divided by x plus 2. Okay, so changing the negative exponent to positive by placing it in the denominator. Either solution would be acceptable. Okay. So our second other case is when we have a quadratic in the denominator, or in other words, we have a term that we can't reduce any further than, in this case, something like x squared. Okay, so the highest order within that factor is squared. So let's look at an example of that. In the numerator, we'll have x squared minus 3 divided by x cubed plus 2x. We can factor out an x in the denominator, so it becomes x times x squared plus 2. Okay, we can't factor this any further, so we can still write this as partial fractions. The difference is that the numerator will look slightly different. So if we write this as partial fractions, we have x squared minus 3 divided by x times x squared plus 2. And that has to equal a divided by x, so that partial fraction remains unchanged. Plus, in this case, because the denominator is squared, we have to do a b times x plus c. So we have two terms now in the numerator 1, which is also a function of x. Okay, so that is the major difference, that when you have a quadratic in a denominator, because that's your only factor, you have to have a bx plus c, or a term with x and a constant. Okay, so using this example, knowing how the partial fractions are set up, let's go ahead and solve it. I'm going to show you a slightly different way to solve for the constants a, b, and c because of this addition of an x term here. So it starts off the same. We multiply both sides by all of the factors, so x and x squared plus 2, and that's to remove the fractions. So x times x squared plus 2. On the left-hand side, those all cancel, and we're left with just x squared minus 3. On the right-hand side, for the a term, the x will cancel, but the x squared plus 2 will not, so we have x squared plus 2. For the bx plus c term, the x squared plus 2 will cancel, but the x will not, so we're left with just multiplied by x. So unlike what I did previously where we left the brackets, I'm going to expand everything out. Okay? So I'm left with x squared minus 3 is equal to ax squared, okay, plus 2a. That is simply by distributing the a. And doing the same thing to distribute this x in, we have plus bx squared plus c times x. Okay, I'll write a slightly better x than that, and that wasn't any better, so let's try a third time. So now we see the last thing we can do is collect like terms. Okay, we have two terms here that have x squared. So I'm going to combine them. So I have x squared minus 3 is equal to a plus b times x squared plus c times x plus 2a. So you can see I now have two terms on the left-hand side. One of them is an x squared term, and one of them is a constant. And I have three terms on the right-hand side. One with an x squared, one with an x, and one that's just a constant. In order for these two sides to be equal, the coefficients behind each of these must be equal. In other words, on the left-hand side we have x squared, so that coefficient is 1. So that has to be equal to a plus b, or the coefficient behind the x squared term on the right-hand side. Similarly, there's no x term on the left-hand side, so the coefficient behind it would just be 0. So that has to be equal to the coefficient on the right-hand side, which is c. So you can see that c has to be 0. If there's no x term on the left-hand side, there can't be an x term on the right-hand side, or this equation will never be equal. The last one is constants. On the left-hand side, we have negative 3. On the right-hand side, we have 2 times a. So we can simply divide both sides by 2 for this last equation and solve. And if we do that, we get that a is negative 3 divided by 2. So we've already solved for two of the factors. The last factor is only in the first equation here, okay? And we now know what a is. So we can substitute that in, and I'll do it in a different color to make it easier. We get 1 is equal to negative 3 over 2 plus b. So moving the 3 over 2 to the other side of the equation, we get 1 plus 3 over 2 is equal to b. And you can either do this on your calculator and get 2.5, or if you want to leave it as a fraction, you'll get that b is equal to 5 divided by 2. Okay, so that's a different way of approaching solving these. I find it works the best when you have quadratic terms in your denominator like we do in this example. All right, so now going to the other side of this page to finish off our question, I'm going to substitute all our values in to our partial fraction equations that are sitting here up top. If we do that, we get negative 3 over 2 divided by x plus 5 over 2x plus c, which is 0, divided by x squared plus 2. So now we can do the integrals with just these partial fractions instead. So that means it's equal to, in this case, negative 3 over 2, moving the constant out of the integral, times the integral of 1 over x dx, plus 5 over 2, again removing the constant from outside the integral of x over x squared plus 2 dx. Okay? Doing that, now we can actually take the integral of both these terms. So the first term, we have 1 divided by x. Okay, so that just becomes negative 3 over 2 times the ln of the absolute value of x. The second term, you see that we have an x squared plus 2 in the denominator, and we have an x term in the numerator. So that means we can still do the ln function, and I will explain why in a second. You'll remember this from lesson 2.1. So if you do this, you have 5 over 2 times the ln of x squared plus 2. And the one item that we're missing here is, remember, if you take, I always look back at what the derivative is. If you take the derivative of this function, you would have to do, I'll do it up here, 5 over 2, and the derivative of the ln function is 1 divided by what's in the ln function, x squared plus 2, times the derivative of the function inside, which is 2x. Okay, so you can see here that we're close. And in most of these circumstances, you're going to see that you're going to get this type of function. Okay, what we're missing here is we have this 2 that we needed to get rid of, which means we'd have to multiply our final solution here by 1 over 2 to account for that. Okay, then we're adding a constant. So simplifying this, the last piece, we get negative 3 over 2 times the ln of x, the absolute value, plus 5 over 4, combining those two fractions, ln of x squared plus 2, plus a constant. So you're going to see that this type of integral, okay, is going to be what you're going to get typically when you have a solution that looks something like this. Okay? If your item in the denominator was, let's say, x squared plus x plus, call it 3, and you had an x term in here, that's when you would see a constant c here. Okay, in our instance, since we didn't have one, there was no constant c. Okay? So let's look at our second example, having a quadratic factor in the denominator. So evaluate the integral of 2x squared plus 1 divided by x times x squared plus 1. Okay, so the first thing we notice is the denominator's factor, and we can't actually factor it any further. X squared plus 1 cannot be factored. It can't be x plus 1 and x plus 1, and it can't be x plus 1 and x minus 1. Okay, it can't be those factors. If you multiply them out, you will not get x squared plus 1. So this is fully factored, and we have a quadratic in the denominator. So writing it just like we did in the last example, we have 2x squared plus 1 divided by x times x squared plus 1 must be equal to a divided by the first factor, x, plus, and the second factor is a quadratic, so our numerator has to be b times x plus c divided by x squared plus 1. Okay, you saw from the last example, the reason for that is when we start to do the integral of this, remember, you have to take the derivative of whatever's inside that ln function, and you're going to have some function of x. So that's why there's an x term sitting here in the numerator. So just like we've done for all of the examples for partial fractions, to remove the fractions, we're going to multiply by all factors here. And x times x squared plus 1. On the left-hand side, these will cancel. So it just becomes 2x squared plus 1. On the right-hand side, we have a times just the x's cancel. So we have x squared plus 1 remaining. And plus bx plus c. And in this case, the x squared plus 1 cancels, but not the x. So we have multiplied by x. So again, I'm going to expand out all of these factors. So we have 2x squared plus 1 is equal to ax squared plus a. Again, just distributing the a. And working the other way and distributing the x, we get plus bx squared plus c times x. So now I'm going to just group like terms like I did previously. So we have 2x squared plus 1 is equal to a plus b times x squared plus c times x plus a. So just like I did in the last example, now I'm going to equate the coefficients of each. So for x squared, we have that 2 on the left-hand side must be equal to a plus b. For the x term, we don't have anything for x on the left-hand side, so that means 0 must be equal to c. So we've solved for our first factor here. And our last one, we have 1 on the left-hand side must be equal to the constant on the right, which is just a. So now we've solved for the second factor. So our last factor b is only in the first expression here. So if we substitute in what we know for a, we get 2 is equal to 1 plus b. So b must be equal to 1. So we have all three factors now, and we can now substitute them into our partial fractions. So we have, for the first one, we have 1 divided by x. And for the second fraction, we have x plus 0, because c is 0, divided by x squared plus 1. So we have our partial fractions now. We can write them as integrals. So if we do that, we have the integral of 1 over x dx plus the integral of x over x squared plus 1. Okay. Again, you'll notice we have an x squared term in the denominator and an x in the numerator for the second term. It's still going to integrate to ln, okay? But what we have to keep in mind is what the derivative of this function is in the denominator. Because if this becomes the ln of x squared plus 1, the derivative of that is 1 over the item in the ln function, x squared plus 1, times the derivative of what's inside that ln function, which is 2x. So you can see in our original expression here, we have an x term, but not a 2. So to remove that, we'd have to multiply our final integral by 1 divided by 2. So knowing this, our final answer then becomes, for the first expression, the 1 over x times dx, it's the ln of the absolute value of x. For the second expression, remember we have to account for that too. So it's 1/2 times the ln of x squared plus 1. Okay, again, the absolute value. And lastly, we can add a constant. So remember, when you're doing this, if you're unsure of the step I'm taking, try it and then take the derivative of this. Okay? If you take the derivative of that function, you should end up with the same partial fractions that we've calculated. If you do not, then that means you made a mistake in your integral. Usually it's a minor one. All right? So that was all I had for this. This was the second part of our partial fractions lecture. These are the practice problems. Again, I recommend you do these practice exercises. It's going to really help you not only improve on your ability to do these types of integrals, but make you faster at doing them. The faster you do, the more often you do them, the faster you'll get, because you'll start to see some of the repetition that happens. Okay? If you have any questions, please ask in the tutorial or just send me an email. Thanks, everybody.